be able to talk a little bit about WebRTC. I invite you as this goes along to raise questions and stop me and ask me about things as we go along. We'll have some time at the end as well. So I think with that, I'd like to jump into the heart of the stuff here that I want to talk about today, which is really around WebRTC. And this is one of the new technologies that I see going forward that's going to really accelerate the way things are happening on the web and change what the internet, what's possible on the internet. Over the last, 25 years that we've looked at the internet and been talking about it here over the past couple of days, we've seen the internet completely change the way that telecommunications works, and with voice over IP, with all of the services that come out with ZIP, with things like Skype. But I think that this WebRTC stuff allows it to go to a very different level in allowing people to communicate, allowing voice and video, and also data between various devices. So what I'm going to do today is I'm going to talk a little bit about what WebRTC is. We're going to talk broadly about some of the use cases for it. Then I'm going to dig down into some of the technical details about how the protocols work. And I've tried to figure out how to make this, make the talk work for sort of a broad audience. I understand there's people with lots of different backgrounds, and some of it might get a little bit too much in the technical weeds, but then we'll come a bit higher level out of that and talk a little bit about the standards, how it's getting driven forward, and what's going to happen with it next, what the sort of timeline is for it. So what WebRTC is taking browsers and allowing them to start and do interactive voice and video. That's part of it. Now, we've had video in browsers for a long time. There's things like YouTube where you can go and play a video, but it's not interactive. It's not real time. I can't have a conversation with somebody else. I can't have an application where I'm actually talking to that person, and there's only 100 milliseconds of latency type between the two people talking to each other. We also haven't had data directly between the browsers at low latency. Most of the things with browsers, yes, the data often arrives fairly quickly. You can use an application like Twitter and get live updates pretty quickly, but you're not really guaranteed that, and it's not very good for things where lots of data starts to queue up, and you want the latest data, not the original data in order. So for Internet of Things and sensor-type devices, it's not very appropriate. So what we're going to do with WebRTC is a lot of things that have been done in the past. Yes, there's been VoIP on the internet, but we're going to put that inside of the browsers, make it very deployable, and we're going to allow data as well. So the key parts that are going to really drive this forward and make it change, and I'll talk more about this slide again later, is one is around ease of deployment. So today, if you wrote a new voice over IP application or some type of communication or collaboration application, you'd need to write it for lots of devices, and then you would need to get it out, get it deployed on people's servers, have people download it or download plugins. And all of these things are barriers to entry for them being able to actually go and use it, when really all they want to do is just go to some site or some business application that enables that use it. So the other issue that comes up around is the development. As there are some very excellent platforms out there like iOS and Android and these various desktop type operating systems where we're developing all of our applications for, but you have to develop in a lot of different places. So we're trying to make it develop onto less devices, so you can write it once and use it a bunch of places, and also just make it easier to develop. Right now, developing communication applications takes a large skill set. There's a lot of technologies involved, and it would be nice if it was as easy as the type of things that we put onto web pages. So the goal here is to allow you to build a communication application without understanding all the deep underlying details of how that works, and instead, in the same way that we write some JavaScript code today and put it onto a website, be able to develop that type of simplicity. I think the combination of all these things put together was going to really make this a technology that allows you to build applications much quicker and deployed much more broadly and really impact the internet more. And that's why you see a lot of people that are involved. Maybe they're at companies, maybe they're researchers, maybe they're with various groups, very interested in WebRTC and what it means. Now, WebRTC is part of the HTML5 framework for how we should go forward with this type of environment. It's one of the really key pieces of it because it has to do with so much of the collaboration operations, but there's more parts too. So HTML5, though it looks much like HTML4, and it's backwards compatible with it and stuff, it's really completely different in its mindset. HTML4 was envisioned as a way to describe the layouts of documents and render a web page so it has a certain look and feel. And HTML5 isn't around that. It's around how do we take all the things that you could do in a thick desktop application and make sure you can do those in a web application. So it adds databases, it adds 3D graphics with SVG, and it adds a lot of these issues with real-time collaboration communications in the WebRTC work. So overall, the whole web environment is trying to move from being a way to display a web page to be a way where you can really create new applications and have it be a development, deployment environment where you can build a lot of these types of applications, you can quickly get them out, and you can have them running across really a lot of devices at once. So let me give you an example of, I'll just stay with this internet where we are for now, but thank you. I'll give you an example of an application that's a fairly traditional type of idea of what we might do with WebRTC, which is on a web page, and this could be a web page, perhaps it's a sales page and people want to contact a contact agent, learn more about it. Perhaps it's an application where you're trying to reach an expert, perhaps a medical expert, or you're trying to do remote education. You have a web browser, and right inside of that web browser, you can directly get a voice and video call that is linking back through to some other expert that you're talking with that is using perhaps a more traditional type of phone system. So that's some of the types of applications people are thinking about it with it. Another class that they're thinking about and starting to develop are ones that are really around how do we just have a browser-based communication program. So today people have used things like Skype or Hangouts, Google's Hangouts, and these are all excellent applications in that they allow lots of people everywhere to communicate with each other. But how do we broaden that out so it's got a much deeper reach and that you can bring in specific type of applications? And that's one of the areas that WebRTC is going. So those companies, Google and Microsoft, are working on this as well to try and figure out how can they get this into the browser technology so that they can build those types of collaboration applications. Cisco's very interested with our WebEx application. We want to do those same type of applications. And we want to all be able to build those applications and deploy them out to users without having plugins that have to be downloaded, without getting security violations around that, without having to hope that somebody has the right thing installed on their computer. Just anywhere that there's a browser, have it work. That's really the vision of where we're going for. Now, there's lots of issues around that. There's lots of standards work that needs to be done, and there's a lot of implementation to make that drive forward. But that's why people are excited about this. So when you start thinking about all the places that can be used, it's probably the applications we can't think of that are the most interesting. I mean, the things on the internet that 25 years ago, what people imagined it would be today wouldn't have really come up. But I think that where I see some of the interesting things coming today is anywhere where you're interacting with somebody else, you're dealing with content that they may have created, or you're playing a game, or you're doing some sort of business application. If you can bring real face-to-face communications in that in the sense of voice and video, that's a place where it can be improved. So I think we'll see the social networking type applications incorporate this in. I think we will see games incorporate this in. I think there will be games where the video from the other person is displayed as live 3D video inside of the game. I think that it'll change our idea of how we can deal with communications like email and those types of work. So those are mostly sort of from a consumer point of view, but I think from the business point of view it'll be similar. It'll be a way of thinking, it'll change the way we do virtual meetings. That's fairly clear from the applications that are coming today. But will it make sense to just have it in the actual business applications that get built? At the point that you're in the actual business application, it will have the communications in it that you need with the person you need on the devices you're using right then and there. So today we think about it, you're doing some knowledge-based task, you're in a design program designing something and you want to talk to something, you go out of that to a separate type of environment. You go use your phone or some other device to contact a person. But if you could just bring that communications right into the business flow, that has a lot of impact. Probably healthcare applications, I think, will be some of the first types of environments where we see this really taking off. Now, the other thing that's important to understand with a lot of the thinking about WebRTC is that in any communication system where you want to talk to lots of other people, the value of any new system has to do with how many people you can reach. So if we designed WebRTC so it only worked with new things and it didn't work with any of the existing communication systems, it would be much harder and slower to deploy because there wouldn't be anyone to talk to. So one of the key things on this is to make sure that it easily works with the existing voice over IP systems, and those are predominantly SIP-based today. So the idea with WebRTC is to use the same media, the voice and video, as is used in many of the existing SIP devices, but the signaling is somewhat different. So the signaling would be gatewayed, in this picture it goes through the web servers and across to a SIP proxy and over to an existing SIP voice and video device from a web browser, but the media goes directly between the two of them. And it's key that the media goes directly between the two of them because that's how we get this reduced latency, real-time experience, but at the same time we still want this to work. And this has always been a sort of complicated part of the internet design, is figuring out, well, what's we call it the thin waist of the internet, the narrow part that's common across everything, such as IP, yet still having a broad range of applications and allowing a lot of innovation on top of that. So what we've decided here is that RTP is sort of our thin waist that we're using for communicating the media, but there's a lot of innovation above and outside of that. So I started talking a little bit about the difficulties of deployment in existing type of environments today. If you're going to build an application that works across several tablets, several operating systems of smartphones, across the desktop browsers, there's a very large development effort at this point. We believe with the WebRTC that for a certain class of applications, it'll certainly be easy to just write it as a web page effectively and use it in that type of environment. So we've seen programs like Twitter deployed across a large range of devices initially just as web pages. I think the same thing will be possible here. Now, I'm not predicting a future where all of these other applications will be built in a WebRTC environment. I think that there are web environments and there'll continue to be applications that are downloaded. They'll both go forward, but this is going to be an important way to get it going quickly. So this is probably a good stopping point for me to see if there's any questions that have come up. I'm going to start digging into the architecture a little bit here and hit some of that stuff. Any making sense so far? Okay, thanks. So from an architecture point of view, the way browsers have been thought about previously is client-server, right? The browser is talking to the web server and it's getting the information back and forth and it just talks to it. Now, when we send a message with Twitter between two web browsers or an application like that, Facebook or something, it's going up to the web server and then back down. And there's a lot of latency that's caused because of that. And it's fine for if you want something to arrive in a couple seconds, but it's not really good for this interactive real-time communications. So one of the biggest changes to the web architecture that's happening with this work is to allow the browsers to directly send data between each other at the same time. And this can be voice and video is predominantly what I'm talking about today, but it can also be data as well. And this becomes particularly important when we start talking about large sensor networks and some of the things that you might do with Internet of Things to send data between these. So that's our sort of first approach, and that had a lot of implications of how do the two browsers find each other to talk to each other, how do they figure out how to get through NATs and firewalls, and we'll talk about how a bunch of the pieces of this work as we move on. At the same time, we want to make sure that you can talk to a web server, which then perhaps gateways the data over to an existing communication system. And I used a SIP proxy in this case, but it could be a PBX or any other type of device, and then down to an existing IP phone that will send voice and video across over to the actual browser application. So that connection to the existing ones as well. Now, when we look at this, there's a bunch of issues that come up. Firewall and NAT traversal, and I'll talk about those a bit. The security of how this all works, how you know you're talking to the right person, and it's not all being intercepted, and what to do about legal intercept. And federation, it's much easier to design a system where you're just trying to build one little island that only talks to itself, but that doesn't, it scales to a certain degree, but it doesn't get the same type of broad communications that we'd really like to see this move to. Issues around congestion control of real-time traffic. We were playing with the wireless network here earlier today, and we were seeing like 61% packet loss or something. How you work in those types of environments. There's a lot of privacy issues involved with this. There's privacy on the who's talking to who. There's also privacy on, we're now going to enable browsers under certain conditions and the user's permission to turn on a camera and record whatever's going on. I mean, what could possibly go wrong with Facebook being able to access your camera? I mean, there's lots of issues to deal with those types as well. So I'll talk a little bit about how we address some of these at the protocol levels. The first thing to understand as we start digging down into the technology is that there is a JavaScript application and some HTML code that's been downloaded from the website and is accessing the components in the browser. And that code, though it's running on the browser and the browser is somewhat trusted, it is not particularly trusted. It's really easy, it's way too easy, in fact, to get bad code running on people's browsers. Because even if they're only going to websites that you'd expect to display reasonably, content that wasn't malicious in any way, the problem is most of them are displaying ads. And lots of people can buy ads. So you can get malicious content displayed as ads on websites that would have no intention of displaying malicious content. And now suddenly a lot of people are running that content in the browser. So we don't really treat the JavaScript as particularly trusted in any way. And that's one of the issues in designing this versus other systems. Now, as we move down into the browser, there's a bunch of components of it. There are the device access to access the microphones and the cameras. There is RTP to send and receive this voice and video over the internet. There is the encryption and the security components of it. There is the codecs for compressing the voice or video. And that's one of the big issues in all of this work is common codecs, such that two browsers can be sure they'll talk to each other. And then there's the way we negotiate that. There's also a whole DTLS SCTP section that deals with transferring the data as well. So there's a protocol called SCTP that's being used to transfer the data directly between the two devices. I'll talk a little bit more about how that's all protected with DTLS later. So those are the main components that are inside the browser, and they're going to be used, and I'll talk about how some of these protocols work across the wire and the type of standards work that's going on around them to figure this out. So jumping into these network protocols, I'm going to work from sort of the media layers up to the higher level ones a little bit. The first thing that's happening is we need some way to encode and compress the audio going across the system. So the IETF has chosen 711 and Opus as the two mandatory to implement codecs. And let me highlight the word mandatory to implement. We'll get to this in a second. The system allows for new codecs to be added, or a browser to have any codecs it wants, and both ends negotiate with each other to understand what codecs both sides have, and then pick the best ones that they can use. But we need to have some common baseline that we know both ends will implement, so that you definitely have something to fall back to actually talk. And 711 is a very common one used across, it's a very basic codec that relates to, that gives us sort of telephone quality, the traditional PSTN telephone quality. And Opus is a newer codec that was standardized by the IETF that has wideband voice and fairly high quality characteristics. So those two codecs were selected for the audio. With the video, this is one of the biggest debates going on right now, is which video codec it should be. And two of the browser vendors, Mozilla and Google, currently prefer VP8, while Apple and Microsoft prefer H.264. So there are many discussions about the relative quality of them and about whether there's widespread hardware support for H.264 and there isn't for VP8 and these types of issues. But probably the biggest issue that will really determine it one way or another is patents. So the licensing of patents for H.264 is fairly well understood. People know what they need to pay for that, and there definitely are patents. When we move for VP8, some people are claiming that there are very few patents on VP8 and that Google has managed to license them to everyone. And other people are claiming no, that they have IPR that applies to it, and there's actually ongoing lawsuits on it. So it's really weird, but this is going to have that aspect of the patents is going to have a huge impact on the success of this work, on which codec is chosen. And if we can't agree on some common codec that is widely implemented between all the browsers, this work will not in the end be successful. So that's a sort of key piece of the work going forward. Moving up from the codec work, we have the way that the media is actually transported, and the way there's a protocol called Real-Time Transport Protocol, RTP, and this is the primary protocol that is used in existing H.323 and SIP devices. So we're reusing that same protocol, and there's a secure encrypted variant of it I'll talk about in a second called SRTP, and that's the key protocol that's been selected. And here again we get into a sort of interesting set of debates. Traditionally, the IETF has designed both encrypted and non-encrypted versions of its protocols with the assumption that the extra computational cost of doing the encryption you might not want to do, so they'd let users choose which ones they wanted to deploy. Here there's a large argument in place that it's at this time there's really no need for an unencrypted protocol. And that there will only be an encrypted version of it. So that's another one of the debates that's going on. Should there be, everyone agrees that there'll be an encrypted version of it, but there's some debate of should there also be a non-encrypted version of it. So anytime we start talking about encryption, it turns out the encryption's the hard part, or the easy part, it's the keying and how to set up the keying material that's the hard part. So the protocol that's been chosen as a starting point here anyway is DTLS. Now, TLS is the transport layer security, and it's the way that we encrypt all of our HTTPS connections. And there's a form of it that runs over UDP called datagram TLS, and that's what's being used here. So it uses the same sort of public key and certificate type approach to setting up a secure channel and the keying material to encrypt the SRTP. Now, this gets us to the point where we have a fingerprint of the certificates, and we understand how to communicate, how to check that a channel is encrypted. Later I'll talk about how we bind that to an identity, because really having an encrypted phone call but not knowing who it's encrypted to doesn't really help very much. You need to know the name and identity of who you're talking to, or else you don't really have a secure communication. You might just have an encrypted communication to the attacker. But we'll come back to identity at a higher level. I think from here I want to talk about the NAT and firewall traversal. So some of the earlier presentations today, people were talking about the overall difficulty of, the difficulty that NATs introduced and how IPv6 would make this a lot easier. That is so true, and the voice and video people have had to deal with this really a lot, particularly when we're talking about two different devices that are both behind NATs that want to directly communicate with each other. And that's the case we have here. We have two browsers. Often they'll be behind various NATs. in people's homes now, we're finding multiple layers of NATs, followed by carrier-grade NATs in some of the carrier networks, and it's a big mess. So the protocols that we're using to deal with this is this ICE protocol, and it's a combination of a couple stun and turn. It uses some sub-protocol stun and turn, and I'll talk about each one of these in turn and explain how we use this to get through NATs and firewalls. The basic approaches that have been tried over time to getting through through NATs is, first of all, you have some local IP addresses on your machine. You might have a v4 address, you might have a v6 address. Those might work, okay, in some cases. Perhaps you have a global public address. Perhaps you're talking to someone behind the same NAT, and that IP address will work. So there's those classes of addresses. Then there's a class of addresses that are on the public side of the NAT. So these addresses can be discovered, and I'll talk about how we discover them in a second, and they'll often work. Now, there's probably sort of 5 to 10% of the time, depending on how you do it, where the two NATs can't talk directly to each other, even if you know their public addresses, because of just the way the NATs were constructed, and they don't really follow the IETF suggestions around NATs. So for those types of environments, you need some type of relay server where you can actually send the traffic up to a relay server, and then it'll send it on to the other side. And turn is the protocol that's used for these relay servers, so that's a third type of address. So the first thing we do is we gather all of our existing addresses on the actual machine, v4, v6, whatever might work. Next, we try and discover the outside address of the NAT. And the way that that's done is using this protocol called stun. The way stun works is you send a packet out to a public stun server, and that stun server tells you the address that the packet appeared to have come from, and that'll be the outside address of your NAT, and it'll give you the port and IP address on the outside of the NAT. Then we use another protocol called turn, which is just a tunnel protocol effectively that allows you to go out to this relay server or the turn server in the internet and say, give me a public address on the turn server that other people can reach me at. And I should say an address and port to get that. So the first stage of doing ICE is you gather all of these addresses that might work for you. You get your private addresses, you get your NATed addresses, you get your relay server addresses that could work, and you pass them all to the other side. The other side does the same thing. It discovers all the addresses that might work, and it passes them back. So now both sides have a bunch of addresses that might work to contact the other side. And they do connectivity checks on each one. So they effectively send a ping to each one of these addresses and try and get back an answer. And the way they do the ping is not using ICMP and the traditional ping approach, but they use the stun protocol to send a request and get back an acknowledgement. And the only difference of it is that it allows you to have a password and a stun ID on it that allows you to check that you got a ping from the correct person that you expected to be talking to. So this is the approach that we're going to use to set up through NATs and firewalls on the browsers. Both browsers gather all of their addresses, they exchange them using the web server to exchange them, and then they try all of them and see which one they can get a connection on. We found, depending on geography, that basically probably somewhere between 90 and 95% of the devices behind NATs will be able to set up a connection directly between them without using a relay server. There are some countries, Switzerland for example, is particularly bad, where they had one of the main service providers there had deployed NATs all from one particular vendor that didn't support this very well. So in some countries the rate drops below 90%. Switzerland's an example of that, but most countries it's fairly consistent. It does vary somewhat by geography, and it's largely due to who the prevalent residential NAT vendors were in the area. And we're seeing over time it sort of somewhat improve as people start to understand the impact of that and drive to NATs that work better. So that makes sense about how ICE and stun and turn work. Okay, so, feel free to ask me questions as we go along here. I'm going to switch to a separate topic which has to do with really the issue of changing the web architecture to allow the browser to talk to things other than the web server. So traditionally we got a web page. It came from a given web server, and really the browser could only easily talk back to that same web server. We called this the same origin policy, and there's ways like cores to make exceptions to it to talk to other web servers, but for the most part the idea was a web browser could only talk to where the data it was displaying had come from. Now, this was pretty important because we're all running web browsers inside of an enterprise or some sort of firewall type environment, and we don't want this, if I accidentally display an ad from some malicious person, we do not want that ad to be able to form a connection from the web browser over to some, maybe a database server or something like that inside of the enterprise behind the firewall, because the browser is running behind the firewall. So that's why the browser is designed that way. Now, the problem we have here is we very much want to be able to form connections to the other devices directly. So if there's another video phone that is inside of an enterprise firewall, we want the web browser to be able to send media directly to it. That's how we get this low latency, real-time experience. But it has, it had this security problem. So, what we don't want to have here is an attacker to be able to send some HTML down to the web browser and have the web browser thinking it's forming an RTP connection to another video phone, but in fact having it sending DOS traffic to a database server inside the firewall. So the approach to this was to basically make the browser very carefully go and talk to the other, so the web page says, hey, I want to talk to this other IP address. The browser itself actually sends a confirmation packet over to that device and says, look, are you involved in this communication session with this voice and video WebRTC session, and do you want to talk to this device? And if the device doesn't send back a confirmation yes, then it won't allow the JavaScript and HTML running on that browser to construct any data to be sent over there. But if it does, then it decides, yes, it's not the database server, it is an actual IP phone involved in this particular WebRTC communication. And at that point, it will allow the SRTP and data communications to be set up between the two. So this type of media consent is what it's been called in the standards, has been a real one of the thorny parts in designing this. The actual protocol that's used to do this "do you want to talk to me" response back and forth is again the stun protocol that was used in ICE. It's effectively the same thing. So any device that supports ICE and stun can do this consent protocol with the browsers and talk to them. So the next level that I want to step up to is how do we negotiate all of this? I mean, we've got all these different video codecs and these different sessions going back and forth. So the way that it's being negotiated is using the session description protocol. And this is an IETF standard around describing different video codecs that a device supports, different audio that it supports. You can describe information about what the bit rates and various characteristics of the devices that you'd want to deal with as well. This is the same, SDP is used by SIP, and the WebRTC work has just incorporated that wholesale and is using the same sort of protocol for doing all of that. There's some extensions people are talking about doing to it, most notably around what we're calling bundle, which is a way of reducing the number of ports that are needed for the communications. So traditionally SDP would have put the audio and the video on different UDP ports, and there's ideas here about how to collapse them onto just using one port. And part of this, there's a bunch of reasons for this. Part is the time to set things up, but the other issue is, as we see, I was listening to the talk earlier about, IPv4 addresses are running out and people are using as NATs as a way of trying to work their way around that. NATs really allow you to trade some of the port space and use them as addresses. But when you start talking about carrier-grade NATs and very large-scale uses of that, if you want to give all of your users 1,000 ports or something, there's only so much amplification that NATing actually gives you to your address space. So we're trying to think about that and reduce the number of ports that we're using there as well, because that's a sort of important space that's also running out. Probably one of the most difficult problems that we're moving to is identity. And there's been a strong authenticated identity has always been a frustrating topic on the internet. I mean, we all wish we had email that was easily encrypted. I mean, there was PGP and S-MIME both took attempts at binding email and giving you a way to provide an identity bound to it and encrypt it and check that it was encrypted to the right person. And those have not taken off wildly successfully. I don't think anyone would claim they're all that successful, partially because of the difficulty of using them. And at the same time, we're watching over the sort of last 5 years the rise of some of these very prevalent identity services like Facebook, like Google, which lots of users are using to authenticate to many websites. And at some level, that's very appealing, that we have these proof protocols that you can make a federated identity service. OAuth is an excellent protocol for this. And at the same time, would certainly like a design where it was easy to have a lot of identity providers. I mean, the idea that there'd be only a couple major identity providers for the internet and that all of our security would rely on our trust in those identity providers is not a very appealing vision of the future to me anyway. And certainly to some of those identity providers it is, but I'd like to have a much more federated, distributed version of that. So what we've been trying to do in WebRTC is recognize that identity on the internet is changing really rapidly right now, and there's a lot of different approaches to it, and we have to be a little bit future-proof to various different ways it might work. The OAuth, or in particular the OpenID Connect variant of OAuth, is the one that if I had to bet which one was likely to be really successful over the next 5 years and meet a wide range of needs, that would be the one that I personally would bet on. It's the ones that we see a lot of vendors, including Cisco, betting on as the major protocol for identity going forward. So I'm going to do this example using OpenID Connect, and then in a second I'll talk a little bit about how it's future-proof for other things. So the basic problem is I'm going to set up this encrypted connection, and the encrypted connection has a fingerprint associated with it, and I want to be able to communicate that I really am the person bound to this fingerprint and pass that to the other side, and they can check that the person who claims to be talking to them really is the person the media is encrypted to. So the first thing that happens is Alice is going to call Bob in this example, and Alice logs into her OpenID Connect provider through whatever mechanisms Alice uses to log in. I mean, it might just be a simple password type approach, or it might use two-factor authentication of some sort. It doesn't really matter. That's just between Alice and Alice's identity provider. Alice's identity provider signs an assertion that says, yep, Alice is currently calling Bob, and here's the fingerprint of the media for that phone call. Alice passes that assertion all the way over to Bob, and along with it comes the URL or the way to contact Alice's identity provider. And Bob can go and talk to that identity provider and verify that this assertion is a valid assertion from that identity provider, and then can check that the fingerprint that's being asserted actually matches up with the fingerprint that they're seeing in their DTLS SRT communication, and at that point has a reasonably good idea that you have a secure call to that identity provider. Now, there's a bunch of important things to notice about this. One, Alice and Bob didn't have to have the same identity provider. So if my corporation wanted to stand up, or my employer wanted to have an identity wanted to be an identity provider for the addresses in it that it owned or outsourced, that would be fine. It could do that. I have a personal domain of IM at fluffy.im, and I could put up an identity service on that. There's a lot of different ways it could happen. But most importantly, different people can choose their own identity provider, and they can have ones that they trust. So that's one of the important parts of it. The other thing is that really it was a pretty generic thing that I was describing here. It's a generic assertion, a generic way of getting the assertion. So yes, Alice and Alice's identity provider have to have a good understanding of what they're doing, of what protocols or approach they're using, but for the most part, it's a pretty generic assertion that gets passed and checked to the far end. So that's what we're trying to do in this WebRTC work, is allow JavaScript to download and be able to verify these assertions from the actual identity provider, and make it so that if some other protocol came up 7 or 10 years down the road that replaced OpenID Connect, or some given environment wanted to use SAML or some other protocol for their reasons, they could do that. This is a very flexible identity framework. It's probably one of the largest changes to WebRTC from anything that's been tried before from a standards point of view, and it's one of the real innovation areas. So definitely an area worth, if you're interested in that type of research and some of the privacy aspects of it, it's worth digging into and understanding a little bit, and there's probably some interesting research topics there of how it goes forward in the future. So I'm going to totally switch topics here for quality of service for a second. So this has never been a topic that's worked very well across the internet. There's been various approaches to it inside of an enterprise or inside of somebody's home, but we've never made it work particularly well from one large service provider in one country to another service provider in another country. The approach that we're going to take here is a pretty minimal level approach of use these QoS markings, diff served code points in particular. We know there's lots of places where they won't help in the slightest and they'll be totally ignored, but it's better than doing nothing is about the approach that's being taken. And they probably will be able to help on wireless networks, on some enterprise networks. Probably they'll be able to help in lots of places where there's a home access point on the traffic going up the uplink to the service provider. On the downlink direction, they probably won't help much. But often we're seeing the congestions happening on the uplink side instead of the downlink side, just because the uplink bandwidths are usually much less than the download bandwidths. So that's the approach that's being done there. It's no one thinks this is amazing or brilliant. If people have better ideas of how to deal with QoS across a very global type of network and what to do with that, the IETF and W3C would definitely be interested in hearing about those types of approaches and what to do with them. The similarly related to this is congestion control and rate adaptation. So TCP has a very nice congestion control approach, works very well, and it has worked fine for web pages. The existing voice over IP stuff that's deployed across the internet today, for the most part, doesn't actually do congestion control, or it does it at the most minimal of ways. It tends to use as much bandwidth as it thinks it needs, and hope that works, and if it isn't working, hope that the audio or video is so crappy that somebody hangs up the call. It's like relying on a human for congestion control. It's not a really very, this is a design that no one would have ever approved, but there it is. It's been deployed and out there. That's how voice is generally done on the internet today. There's some exceptions to that. There's some products that have some sort of advanced congestion control on it, but voice for the most part isn't. Now, it's worked out fine. It's gotten away with that purely because it was a small enough percentage of the bandwidth that it could do this. That's probably not going to happen with video. If we have HD video becoming quite prominent and used in lots of different places over IP for this type of interactive stuff, it won't work. So we need new congestion control approaches. And it's a difficult problem in that slowing down is actually not too hard. There's some simple and good approaches to slowing down. Speeding up turns out to be harder. deciding when you've slowed down too much and you should start speeding up again. And we're working on environments where the network conditions actually shift very quickly. As other people come on and start doing stuff, you need to be able to interact. You need to be able to adapt to that quickly. At the same time, you're competing with TCP traffic. And TCP was largely designed to deal with maximizing the bulk throughput in a fair way. And it does a great job of that. But one of the things that it does is it builds up a lot of latency in all of the buffers. And this is really particularly bad for the real-time communications. For the real-time communications, what we wish we could do, we're not so much concerned about the bandwidth. I mean, yeah, we got to fairly share the bandwidth. But we also want to keep the latencies down. And TCP tends to push all of the latencies on every link along the way up to be fairly high. And you've probably heard some of the buffer bloat talks that have been happening over the past few years. This is one of the real issues there. So what we're trying to do is figure out a way to have the interactive real-time traffic fairly compete with TCP and have it so that TCP doesn't use up all the bandwidth and that the real-time traffic doesn't use it all up. There is probably no really compelling, great algorithm that works super for this today. There's lots of people talking about various things. There's some stuff shipped and deployed. There's a working group at IETF that's trying to work on this, but that's probably one of the areas which is ripe for some research today. That said, the browsers are shipping stuff, and they're trying to take some simple algorithms to do this, and working fairly well at that, though if you have a TCP link that is really trying to use up a lot of the traffic, the browsers get pushed to a very low amount of the overall bandwidth by that. So I think this is, I've been talking about the networking protocols here for a second, and I want to switch to a different side of it, which is a little bit, what's it like from a programming point of view and the APIs for this. So I mentioned we're trying to make this easier. And let me start with a little bit of a code example here. So this is a simple example that allocates a camera and starts getting video from that camera and then displays that on a video tag in the page. Okay, so the actual code here in the sort of first line is it's finding the video element, which was labeled vid in the HTML script, on this HTML5 page that's being displayed. And on this video element, it's going to eventually set I'm going to start. Stand down here. Oh, I know, because I have a mic. That's why. Sorry. So the video source of that is set to this URL that is set in the got stream callback. Laser pointer for me? Thank you very much. So the first thing is to get the actual video, find the video tag. Then the second thing is that when the actual start button is hit, and I'll show you this in a little bit, we're going to call this new get user media call. And this is one of the things that's being defined by the W3C and is the really new part of what's being done here is the get user media allows you to get access to a camera or to a microphone. And here we're saying we want video. And we're providing two callback functions, one on success, one on failure. In good web fashion, we're ignoring all errors on the failure one. And on the success one, all we're doing down here is setting the video tag source to be whatever was returned from this stream that we just got here. So that's pretty much the complete code for the web page I'm going to try and go and display here. And we'll see how my internet connectivity luck works. And I encourage people to go play with some of this stuff sometimes later. So we've got a start button here. When I click on it, it's going to run that function. Now, the first thing to notice here is the browser has actually popped up a permission dialog with allow and deny to access the camera. And that is in the actual browser Chrome. It's under browser control. It wasn't like the JavaScript page could spoof that in some way. So I'm going to hit allow here. and there we will have live video in that page. So this is definitely well within the ability of your average web programmer. There wasn't a lot of voice or video knowledge or anything like that to be able to get those type of data and connect them up. Similarly, there's PC streams that's called a peer connection stream, where there's an object that you form which is a connection to a remote side, and you add the streams to it, the voice and video streams, that allows you to set up voice and video between two browsers. And I'll show a demo of that in a second, but let's sort of look at another type of thing we can do here. So once you get the live video into the browser, there are a lot of other types of processing that you can do on it just using HTML5, or sorry, just using CSS. So this is an example here where I'm going to allow access to a microphone, and it's actually reading the data. It's capturing the data from the microphone, and it's bringing in that into a JavaScript application, which is just doing a spectrogram of it that's all computed in real time in JavaScript. Now, I'm not arguing that really we're going to start doing DSP signal processing in JavaScript, okay? But we do have access to this type of data, and what's been possible with it has been quite surprising for people. People have actually implemented H.264 video codecs for a low resolution data in JavaScript. So JavaScript has turned out to be much faster than people thought it was going to be, and there's a lot possible there. And I think we'll see things where people start doing some of the processing locally and playing with it that way. The nice part about this is that allows you to do a bunch of the processing locally and send a lot less data over the network. So I think with that, what I want to try and do here is go to one more demo, and all the code for these demos is around and live. And I am going to see, you want to try joining the room? Never mind my firewall here, that's just me. Okay. So we solved a bug in that Chrome has a bug in it right now that evidently on the device driver for that computer it's upside down. But that was solved by a clever rotation. And this right now was a pretty small amount of code, and you can see it's coming from the back room up the front. I think we're running that over a cellular connection off a hotspot right now, and the data is all going directly between us. So this was, from a web server that was, I guess that one's in, I think that one's in California somewhere that came from. But this video data, you can just see from the latency and the real time of it, it's quite quick back and forth, and it's not going all the way to California and back. It's just going across our local network, and both the devices went up and set up that web connection through the protocols we were talking about earlier. So this demo works today in Chrome and in Firefox. It doesn't work in IE or Safari yet, and I'll talk about that in a bit. But I think you get the idea, and we'll send out these slides later and these types of links, and people can go back and play with it themselves and get an idea of what it all looks like. Let's see, I'll hang up on that for a second here. Questions about that type of environment or what it looks like? Okay. So I want to take a little bit of a second to talk about the standards. So the standards for WebRTC are being done by two different standards organizations, W3C and IETF. Now, both W3C and IETF are standards organizations that work under the umbrella of ISOC. They're both heavily involved with that and largely funded by ISOC as well. And they work together on quite a few protocols over the years, but particularly in this case, the IETF is doing the work of how the protocols over the wire, how the data gets transported over the internet gets done. And the W3C is working on the parts of it that have to do with what's the API into the browser, how will you interact with this, how will the privacy and access to the camera, those types of issues work. So the W3C is doing two key documents on this. One is the access to the microphone and cameras document, and the other, which is called Get User Media, and the other one's called Peer Connection, which is about how to set up the connection to a remote browser peer. And I'm one of the co-authors on both of those. Now, the IETF has, I don't know, it's probably 8 or 10 documents now, drafts going on that have to do with the overall structure of the architecture, the requirements and use cases, how the security works, how various parts of the signaling protocol works, and how we'll use RTP and SDP and DTLS and SRTP and these protocols I was talking about earlier. So, all of those are moving along sort of in progression, and I'm one of the co-chairs of the working group at IETF that deals with this. Now, it's always complicated to keep multiple standards organizations sort of aligned and moving in the same direction, but really this needed those two different organizations to come together to pull something like this off. So that's how the standards are being developed. In a very standards organization confusing way, the two working groups doing this, the one at W3C is called WebRTC, and the one at IETF is called RTCWeb. This, I don't know who thought that was a good idea. Actually, I think I was one of the people who thought it was an okay idea at the time, but it has not turned out to be a good idea. It's confusing terminology. So be aware of that. If you hear both those things, they're the same thing, or they're working on the same technology. And most people at this point have just decided that the name we'll use for the technology as a whole is WebRTC. So this is, has some of the pointers and links to some of those protocols I was just talking about in the documents and what's going on with them. Now, the state of the implementations, well, actually I should say something about the state of the standards. These standards are, a lot of the key things at a big macro picture are nailed down. People understand basically how they're going to work, and they're working on some of the details. But a lot of the details are still really missing. Like how to have reasonable error reporting codes is not defined on most of the things. Lots of the corner cases, what goes wrong, how you report what's going wrong. So basic demos like I just showed worked, but the type of things you need to build a full application that dealt with all of the things that could go wrong and how to correctly report them and recover from them aren't there yet. So there's still quite a bit of standards work to do on that. There are probably there's a bunch of documents. They won't all be finished at the same time, but some of them will probably be starting to be finished a year from now. Some of them are probably more 2 or 3 years out before they're all done. So then we get to the actual implementations. So of the 4 major browsers, Mozilla and Google have working implementations right now of this. Now, there's lots of limitations to those implementations. Like we were just watching Google's. They'll only set up one video stream right now. They're obviously working towards supporting multiple video streams. That's an important thing for them and others down the road. But it's early. They've gotten some stuff working. Now, it's also the desktop browsers are what was done first. The mobile browsers are coming. They always lag a ways behind the desktop browsers. They're just a little bit more complicated, and people got it working on desktop first. Now, when we move to Apple and Microsoft, it's much harder to predict. With Microsoft, we know that they actively followed this. They've talked about supporting it. We don't know exactly how they'll support it. We don't know. They haven't announced any formal dates for when they're going to have it, which product release it would be in or anything like that. And I think when, a quote from one of the Microsoft people was something along the lines of, we don't pre-announce our products, but they're clearly working on it and moving that direction, and no one knows, or they haven't announced any exact dates from that. Apple is even more complicated. They're very good at being secretive about what they're up to and doing. the Apple people have shown up at the meetings and contribute to the standards and suggest ideas of how it needs to be changed, but no one really has an exact idea of what Apple's release plans are or ideas. My personal belief on this is that when two of the major browsers, representing, depending on who you trust on, representing roughly half the browser market space, and I say very roughly, it's very hard to get good data on this, go and do this. It's such a competitive advantage for them that I think the other browsers will have to do it. So my expectation is we will see all the major browsers support this, but it's hard to guess the actual timing of when that will happen. So, maybe next week at Apple's WWDC, we will see them announce support for this. I'd be surprised, but it's certainly possible. Some people think it'll happen. I think it'll be a little bit farther out before they announce support for it. Get back to full screen there. So, bringing this all sort of back to where we started at the beginning. Why we think this is going to have such a sort of impact on the way people build things on the web is it makes it very easy for a small group of people, or maybe some students, maybe a small company, maybe just a group working inside a company, to really quickly add complex voice and video and real-time data to their application. They can build it, they can get it very quickly deployed across a lot of devices, and they can, it'll work across a large range of devices, and they can push it out to an incredible number of people really rapidly. When they want to come up with a change to it, they can just change it on a web page, and suddenly that's instantly deployed to all of their users instead of waiting for things to slowly migrate and upgrade. So we think that this combination of how it's easy to develop it, how it's easy to deploy it, how you can get to lots of devices, that's really going to create this power to create a new sort of platform to be able to do it much faster than we could in the past and really push this work out. So that's that's very much Cisco's view on why this is so important. I think a lot of other companies would share that point of view of that this is probably one of the most important things happening on the web right now of how it was going to cause that shift. So if you want to find out a bit more about it, there are the specifications I had the links to. There's an excellent book written by Alan Johnson and Dan Burnett. But most importantly is to get involved with the standards organizations and join in that conversation. And it's not that you have to write the standards. That's not the most important thing. The most important thing is getting the use cases and the requirements and what the users need and get that information in. So I've provided that there's the email list here for the W3C and the IETF. And go and join those and look at what's going on with that. So I think with that, I would like to ask if there's any more questions on that, and just to open it up to any other questions people have had along the way about this whole area.
Hi, two questions. One, I was very surprised to hear that quality of service is still an issue. It's been a research topic like probably 10, 15 years ago, right? So two questions then. One, do you think that could be a key blocker for WebRTC to take off if people cannot get good quality video? And then secondly, what, in your view, what will it take to fix the quality of service issue for the internet? Why is it taking so long to fix the issue?
Those are good questions. So let me first say what I think is possible quality-wise without changing anything, and then try and say, well, what could we change to do better than that? So Skype is a great example of something that delivers a very certain level of quality of experience today. Some people think its quality is good. Some people think it's awful. Okay, and I'm trying not. So that quality is easily achievable without changing anything. We know how to do that, and I'm not picking on. Skype does quality about as well as we can easily do without changing anything on the internet today. Okay, and lots of other applications do a very similar level of quality. So many people believe that will be fine. That's all we need. and they often point to Skype as a success point of we're good enough, right? I have a hard time evaluating whether that's good enough or not. That's a human factor, user experience problem. I tend more to think about it, but could we make it better? Clearly there's room for improvement. And I think one of the reasons that's made it so hard to do better quality on the internet is that a lot of the research schemes that came up clearly would be better, but they required, let's say my call is going to go across 3 service providers in 2 countries. They required all of them to deploy whatever the new technology was before anybody got any benefit out of it. And that was this is the same problem with V6, right? I mean, everyone agrees it'd be easier, but who wants to be the first person to move to V6? It doesn't really provide you anything until other people do it as well. So I think that that's one of the difficulties in this is, and this is well known in the research community, I'm sure, but is to try and find schemes where there's some benefit before everyone moves to whatever the new technology is. I'm particularly keen about some of the research we've been seeing in these measurement-based approaches where you try and figure out how much bandwidth you can use and how to reserve the bandwidth in different classes without impacting other people. I'm less thrilled about approaches like RSVP. I just don't really see how RSVP could work. And I mean, I know that's old, but some approach where you went and made a reservation across every sort of step of the way seems very hard to me at this point. I'm keen on the research that takes into account the idea that there's probably large parts of the core of the network where we don't need to worry about QoS and really focus on more of the edge parts of it. And I know that where the congestion is happening has changed over time and moves, but we need to focus on the part where we're having problems. So I would like to see improvements around that space. I think that this is a really large opportunity with WebRTC for the service providers that can really provide QoS, particularly in the last mile of the network. I think that they can get themselves back in the value stream here. And what I mean by that is the over-the-top applications have been having a lot of problems with QoS. And I think that this is a great place where even some website that was running an application could be talking to the browser that is communicating and talking to the local network and negotiating QoS for itself, and at the same time setting up a billing relationship back to the original website, so that the end user isn't the end user is paying the website for a service. You can think about the end user is paying Netflix or iTunes for a service, but that service is then paying the network operator to provide QoS or certain bandwidth things. That's the type of solution that I see the most promise in, is ones that focus on the service providers being able to provide the QoS and a billing relationship that made that all work. Open issue, yeah, I think it's very much an open issue.
Hi, my name is Sukumal Kurtisin from Kasetsat University. I'm just wondering about the WebRTC, the work on the protocols level. You were working on the multiple stream of video, right?
Yeah.
And there been a work done before in the past on the multiple stream or video conference using multicast technology. How that will be reflected on the protocol level for RTC web?
There has been some discussion around that previous work, and people would like to bring in some of the multicast type of work, but it got pushed out to later phases. So the first phase has multiple streams of video, but no multicast at all. It's all
of them are unicast, like point-to-point unicast?
Yeah, so it's all point-to-point in the first version, but people have thought that once the first version is sort of done and the standards are done for that, that they'd like to move on to something a little bit more complex and relook at some of the multicast work. There's certainly a desire of the people building the conferencing equipment to figure out, I mean, multicast could allow it to be much cheaper to deploy large conferencing applications. That's clear. So I don't know what will happen with it, but I think it's an interesting area.
Thank you.
Other questions? Any other? Okay, well, I would like to tell everyone thank you very much. And if there's any other questions I didn't answer, please come and find me afterwards. I'm glad to pass on whatever I can and answer questions about this or other technology that comes up. Oh.
Actually, I wonder if you can explain or make a relation between WebRTC and Internet of Things, because the topic of the talk today is one of the part is Internet of Things. Can you say how it can be applied?
Sure. So they are largely different topics of some of the key problems that are happening in there, but a lot of the when we're talking about Internet of Things and sensors and devices, they're often very much interested in real-time data, and they're creating a lot of data that isn't necessarily stored. Usually you want to get the most recent data, not all of the data along the way. And if you had thousands of sensors that all reported simultaneously some similar key event, how that would be aggregated and displayed up would be one of the sort of key issues to deal with. Now, we've been looking a little bit about using the real-time data protocols on this to allow some of these devices to get data to browsers, since that's often one of the ways that people are displaying the data. So one of the examples that I didn't show today, but had to do with somebody in their house wants to display real-time data of medical sensors or other sensors in their house, that type of information, so that those sensors could communicate directly with the browser that was displaying the data instead of sending all of that data up to a website and then back down. And you might go, well, it doesn't matter when everybody's sending it up and back down. But it does matter when it's really a lot of people. Like when we looked at Google Power Meter project, for example, when you start getting hundreds of sensors in people's houses reporting fairly frequent real-time data across millions of users, it becomes a very difficult task to try and deal with in a centralized way. So this same sort of peer-to-peer approach of trying to make it so that the data itself doesn't have to always go back up to the center of the network, but could be aggregated in browsers and then key bits of it sent back up to the center of the network would be one of the sort of areas where we think that these technologies will touch each other and combine together.
Hello.
Oh,
Okay.
there we go.
Well, actually, I had the question while I was having lunch with you, but I thought maybe it would be a good conclusion to your session, if there's no question here, is that can we ignore WebRTC or RTCWeb going forward? After all, this is an internet session, and we talk about the future of the internet. So some of us are trying to ignore IPv4.
Mm-hmm.
So, we know the answer. So what about WebRTC? Can we ignore it? What do you think are those possibilities to become islands, as some people like to say?
Right. So it's been a complicated question that many of the vendors have had to wrestle with is, would this not happen? Could it just sort of go away? And in many ways, for the large communication vendors, so the Ericssons, the Ciscos, the Microsofts, the Avayas, this commoditizes much of what they do, right? It makes it very easy and cheap to build many of the things that they currently sell. So I think a lot of those companies had to internally think about what was, were they going to help this happen or not, what was going to happen. And pretty much everyone came to the same conclusion, which was this was going to happen with or without them. And I'll talk about the impacts that it'll hit the various different people, but that it was a natural sort of way that the web was going to evolve. It added a lot of features and service that were very desirable, and because of that it would happen. Now they might wish it wasn't going to happen, but it was still going to happen, and that it was going to have an impact on congestion and the other pieces of the web that way. It was going to have an impact on how people thought about NATs and firewalls and where they existed in the network. It was going to have an impact on gaming. It was going to have an impact on media in the sort of interactive communication sense of it. It was going to have an impact about how these other devices on the network and Internet of Things connected to user interfaces. So I think that in the same way that the web has become a really large part of the internet, the web has a huge impact on the internet, even though it's not the only thing happening on the internet. There's a lot more happening on the internet than just web pages. This is going to change really a lot of the things that are running on the internet, and the protocols, and whether this congestion control works, or how QoS works, or how billing works in this type of environment is going to affect the rest of the pieces of the internet. So we see that sort of all coming together. It is also a technology that, for better or worse, is embedded in HTML, and if you don't want to block HTML altogether, it's very difficult to block this. So it comes along with it. You're going to end up with people having interactive real-time communications, and the only way to block that would be to turn off a really large part of HTML and what was done with web pages today, which will be, that would be difficult for lots of people to do. There would be a lot of functionality you'd lose by doing that. So I think that even for places that don't want to enable this type of communications, if they do want to enable web pages and HTML at the same time, it's going to be difficult to block this type of communications with this type of approach. So that's really why I think a lot of the so many people that are focused on building this right now and figuring out what it will look like going forward.
Hi. Okay, I ask you, how do you see the IMS versus the WebRTC for the telco point of view?
Right. So today, as many of the people in the room are very well familiar with, the bulk of the mobile and smartphones are all based on the IMS technology, and there's a fair amount of work going on with making sure that the architecture of this WebRTC interoperates fairly well with what's already deployed with IMS. So this is part of the focus on making sure it works on SIP used in IMS. This is some of the questions that come up around QoS. Can we use the IMS QoS type approaches for the applications running on web browsers? It seems the answer is probably yes to that. So that is one part of the conversation, is how well can these two work together, and they can clearly interoperate. That's not a big problem. That's been pretty well shown at this point. The next level is, can we use the type of services that IMS can provide and leverage those into that world? I believe the answer is yes to that. I think Ericsson agrees the answer is yes to this. We're seeing AT&T and Verizon very actively involved with the design of the QoS being particularly one of the issues in that space. The next set of questions that we have with some of the large mobile carriers is around, well, moving out to the next generation systems, maybe it's LTE, maybe it's one generation beyond that, will WebRTC replace the SIP portion of the IMS system? Can they just still use some IP architecture for their internet stuff and then just use WebRTC to do all of their voice stuff and ignore all of this. And I think that remains to be seen. I think I think for the current generation of technology, no, it's IMS, it's deployed, it is what it is. But for the next generation of technology, I think you need to seriously look at this as a way of doing it. And I think that there was some carriers probably will do that and have a huge cost reduction in doing that. Look at some of the carriers in a country like Brazil. There's a lot of incentives for them to not deploy a whole IMS system, which is a very expensive proposition, and as they rapidly grow, expand just using WebRTC and providing only an IP network. So it would certainly not surprise me to see a future where a large mobile carrier provided only IP and then ran applications using WebRTC on top of it. It also wouldn't surprise me to see some of the large, or many of the, I think that's a small section of mobile carriers. It wouldn't surprise me to see many of the larger mobile carriers too, just doing IMS as they are today and running WebRTC as well. So hope that helps.